Hello everyone, welcome. Today we are very happy to have Professor Sergei Gukov from Caltech, and he's going to tell us about geometry of 0,1 SQCD. Over to you, Sergei.
Thank you very much. It's a pleasure to give this talk and see many of you, many familiar names and faces. So I hope everybody is doing well. And I certainly hope that one day soon we'll be able to see each other in person. So the technical component of this talk is based on joint work with Pavel Putrov and Dupay. And this work is only relatively recent. It's actually from 2 years ago, before COVID, but I guess this COVID time is, depending how you look at it, either goes too fast or too slow, so it feels as if it was just yesterday. But my actual motivation for speaking about it is that recently I've heard a couple of very good talks during this past summer by Sebastian Franco and his collaborators. In fact, one of the talks was here at Caltech a couple of weeks ago, and another is by Miriam Svetic, Jonathan Heckman, and their collaborators. And these talks basically motivated me to think again about two-dimensional physics with very little supersymmetry. So in 2 dimensions, supersymmetry can be chiral. So the most minimal amount you can hope for or have is 0,1. So basically the goal of the talk, aside from some concrete specific statements and so on, is to answer the following question: where can we find these theories? Why are they useful, or why they're interesting? So what's the landscape of such theories? And it's precisely this 2 other papers or works that motivated me to think about this topic again. Actually, these authors, to which I'll jump in a second, I believe have a series of papers coming up. I'm not even sure if their first paper appeared yet. A couple of weeks ago when I checked, it hasn't. So maybe it's still not out, but in any case, we should stay tuned for several papers. And finally, I'm also hoping that this could be sort of a nice present for Abhijit personally. So I obviously miss him here at Caltech, and in our good times, mischievous times here, we were thinking about trialities, and this word is still in the title. And in fact, a lot of what I'm going to tell you is sort of motivated, or there is this older work as part of the background, and hopefully you'll be able to see in what form as we go along. So without further ado, I'll move on to tell you what these people are considering. Sebastian Franco, Angel Rango, and their younger collaborators, who I think are even on a job market this year. So they ask the following question. Suppose you take a special holonomy manifold, spin 7 holonomy manifold, which has a conical singularity, so it looks roughly as such. It's a manifold of 8 real dimensions, and therefore if you compactify string theory, either type 2a or type 2b on such a manifold, you have 2 other dimensions left. And in type 2b, you can place D1 branes, which have 2-dimensional world volume at the tip of the conical singularity. And the typical question we ask in string theory in this setup is, what kind of physics do you find on this D1 branes? So that's a very standard question. And here, if you count number of supercharges and supersymmetries, you quickly see that you expect 2-dimensional 0,1 physics. So that's basically the question these people are asking. And what motivated me to think about it again is that apparently almost nothing is known about it. And to me, this was kind of surprising that first of all, it's such a basic question. And again, in the next few minutes, I'll illustrate that every other variant of this question seems to be discussed quite extensively with hundreds of papers written, but such a basic thing apparently had to wait until 2021. So why and how? And it's not just kind of academic question. There are lots of amazing new physical phenomena that one can expect in this sort of systems. With such little supersymmetry, you can have dynamical breaking of SUSY, all kinds of phase structures, many interesting RG flows with lots of infrared fixed points, their mergers, and so on and so forth. In this talk, I'll basically just scratch the surface. I'll tell you a little bit of what I know about such systems. And even from this preliminary view, we'll see that many of these interesting physical phenomena get realized, and one can only expect a lot more in a more systematic study, which is probably what these people are doing, and which I think is what would be good to study. In case if anyone is looking for a good project, this could be an interesting direction to pursue. So why, again, is this question kind of surprising to me? So if we compare the analogous, this question to analogous situation in 4 dimensions, namely, if we choose a special holonomy manifold to be Calabi-Yau threefold, then again, it's a manifold of real dimension 6. We can compactify type 2B string theory on such conical Calabi-Yau threefold. Let's say conifold is the traditional example. You can pick various orbifolds and so on. Then it has 4 transfer spatial dimensions. You place D3 branes at the tip of the conical singularity, and resulting 4-dimensional now theory also has minimal supersymmetry, minimal in the 4 dimensions, and that's 4D n equals 1. And again, many of the same types of physical phenomena, dynamical SUSY breaking, interesting landscape of RG flows and phases could potentially be realized. And in this case, a lot is known. So that basic example of a conifold that I mentioned as a prime example was studied, for example, by Klebanov and various collaborators. And we know very well what the 4-dimensional n equals 1 theory on D3 branes probing conifold singularity is. It's usually presented as a quiver diagram. So nodes of the quiver represent 2 gauge groups. These arrows represent 4 kinds of bifundamental multiplets, usually called A1, A2, B1, B2. And this is basically starting a point for answering many of the interesting dynamics questions. But in the case of spin 7 manifolds that these people are trying to study, and that I was thinking about more recently, we don't know analogous questions or analogous answers. Rather, the question is fairly simple, that you take spin 7 analog of conifold. In a second, I'll show you what examples are there, and there are quite a few of them. You again place D1 branes, and you ask, what is the effective physics on these D1 branes? By experience with these high dimensional systems, you may think that when there are no odd Betti numbers of a resolution of a conical singularity, let's call it X, to avoid clutter in the rest of the talk, I'll call by X both the singular space as well as its resolution. So when I speak of Betti numbers, of course, I mean the resolution of conical singularity. So one may expect that the number of nodes in the quiver is simply related to the early characteristic of the resolved space. So in the case of conifold, this would be 2. So and then many other examples, this mnemonic rule works. So you could expect that this is true more generally, perhaps even in the case of D1 branes probing spin 7 cones. Again, I'm just stating this from experience. I have no serious reason to back this up. It's not a theorem, but it's an expectation that one can try to either prove or disprove thinking along these lines. So these are a couple of examples of such spin 7 manifolds. Usually they're characterized by the base of the cone, of the conical singularity, and topology of the space that I called X a moment ago that you can obtain by smoothing out or resolving this conical singularity. So one conical metric is like this. By y, I'll denote the base of the cone, and x will be either the cone itself or its resolution. So the conifold in the spin-7 holonomy world is a cone on homogeneous space SO5 mod SO3. So if the cone has to have spin-7 holonomy, then the base of the cone has to be weak G2 holonomy manifold. That's analog of the Einstein-Sasaki condition. That's perhaps more familiar in analogous compactifications on Calabi-Yaus. And this cone can be smoothed out by replacing singular conical point with a four sphere, which becomes exceptional cycle. So if the rule inspired by high dimensions works, then in this system, we should expect that D1 branes probing this particular manifold should have two quiver nodes, very much like in Klebanov-Witten type quiver. Then there is another space. So that's also homogeneous space, SU3 mod U1, which can be actually resolved or smoothed out in several different ways. It has one phase where you create exceptional cycle CP2. And then if again, the same rule that I mentioned applies, you would expect a quiver with three nodes on the D1 branes. Or there is another branch where you create a five sphere, replace the singular point by a five sphere. So that's a very peculiar phenomenon, kind of analog of a conifold transition. And already in these two examples, you see that there is a lot to be said. And these are perhaps simplest examples of conical spin-7 manifolds. There are millions of others, but even in these basic cases, we don't know what the answer is. So it's a good, interesting question. Again, coming back to Calabi-Yaus, analogous question is again D3 branes probing Calabi-Yau conical singularity. Here are the bases, Einstein-Sasaki 5 manifold. And first hint that there is interesting infrared conformal fixed point on such branes probing the conical singularity may be inferred from ADS CFT correspondence. Namely, if you take the number of D3 branes or D1 branes to be very, very large, then you get essentially ADS cross base of the cone compactification of type 2B string theory. In the present case, it would be ADS5 cross this Einstein-Sasaki manifold. And from there, you can quickly read off, for example, relation between central charges of this infrared fixed point and the volume of the Einstein-Sasaki manifold. So again, this in the case of three-folds and D3 branes has been studied very, very extensively. There are hundreds of papers, but analogous question just dimension down, where you have D1 branes probing the spin-7 manifolds, really has not been addressed as extensively, even though you can look at analogous ADS solutions, namely imagining that number of these branes is very large, then you would be looking at a vacuum of type 2B of the form ADS3 cross Y, where Y is this weak G2 holonomy space. And it's a nice vacuum. It would suggest in many cases that there is at least larger inversion of these CFTs. Then the question would be, what if number of D1 branes is small or finite? But at least for a large number, this would be a hint that such theories are interesting conformal field theories. And very little is known, although in unpublished work with Kummer and Waffa, we try to relate gravitational anomaly of this 2D01 CFT. Again, it's chiral, so it's left-right asymmetric. So therefore, left and right central charges don't have to be equal. And in fact, we argue that this difference is related to topological invariant of this weak G2 holonomy 7 manifold called new invariant. This new invariant is defined modulo 48, and therefore you basically determine this gravitational anomaly mod 24. And for this spin-7 conifold that I mentioned a moment ago, it's a non-zero, it's -1. So that already is a hint that there should be non-trivial CFT in the infrared. Okay, So for this manifold, if you ask analogous question in M theory, so this is spin 7 conifold compactification of M theory, then by counting supersymmetries, you get 3D n equals 1 theory. And I already mentioned that, there is a manifold, this spin 7 conifold, which has either resolution in terms of 5-sphere or in terms of CP2 as exceptional cycles. And in fact, in the case of CP2, you have 2 branches. So the whole diagram looks like a 3-prong or three real branches touching at a point. And they have interesting physical interpretation in terms of 3-dimensional n equals 1 effective field theory, where 2 CP2 branches could be interpreted as Higgs branches, and this would be a Coulomb branch of the effective 3-dimensional n equals 1 field theory. On the Higgs branches, the parity is spontaneously broken by either Chern-Simons level in the field theory description in 3 dimensions, or in terms of spin 7 holonomy manifold on which we're compactifying. That's a quantization condition of a 4-form flux that has to be non-zero and give therefore either plus a half or minus a half. And that's what triggers this choice between the 2 branches. This system has more supersymmetry. It's 2 real supercharges compared to what I mentioned on the previous slides. And one may hope that physics of D1 branes probing this spin 7 manifold is somewhat similar, so maybe it shares certain properties, but already from this story, 1 dimension higher, namely 3D n equals 1 physics, one would expect, again, fairly rich, interesting structure of phases, and that's yet another motivation for analyzing the system. So now let me, I try to motivate it from ADS CFT or string compactifications on special holonomy manifolds. But now let me switch to another perspective where I'll try to motivate study of 2-dimensional 0-1 theories entirely from quantum field theory perspective, just as a QFT person. In 4 dimensions, which appeared, for example, in the case of conifold compactifications and so on, we know that there are many interesting dualities and regimes where strong coupling physics can be related to weak coupling regimes and so on and so forth. So this is, for example, famous example of Seiberg duality in 4-dimensional n equals 1 super QCD. What about 2-dimensional analogs of this story? Well, if you lower a number of dimensions, go from 4D to 2D, you certainly have a lot more control over physics, simply because gauge fields don't have interesting polarizations, at least not as much as in 4 dimensions. Conformal symmetries provide much stronger constraints. And for many other reasons, living in 2 dimensions is actually easier than living in 4 dimensions. So you would expect a lot more analytical control. But if at the same time we lower the amount of supersymmetry, and keep in mind that supersymmetry also provides good analytical control, then we can sort of compensate for the simplification by making problem a little more interesting or challenging if lower amount of supersymmetry occurs in 2 dimension compared to 4-dimensional theory. Roughly for this reason, but also motivated by study of various vortex strings and 4D n equals 1 and n equals 2 theories, Misha Schiffman and actually many other people popularized the idea that one should, roughly speaking, compare physics of 4D n equals 1 theories to physics of 2-dimensional 0-2 theories. This is exactly what vortex string would see in 4D n equals 1 theory. And vortex string should reflect many of the properties of its ambient physics. So that's why these two are roughly comparable. And in the case of 4D n equals 2 theories, the fair comparison would be 2-dimensional 2,2 theories. So from this perspective, you would expect that studying 2D02 theories, and I even made a request for 2D01, should be fairly interesting with lots of dynamics, perhaps analogous to what we see in 4-dimensional n=1 physics. And here the natural question then is, what is the analog of Seiberg duality and other dualities and phenomena that we see in 4-dimensional super QCD with minimal supersymmetry? So you might ask, and perhaps quite rightly, why are we talking about it today? As I mentioned, 2-dimensional physics is usually very much simpler. So in particular, in the context of gauge physics, Julian Schwinger a long time ago, back in early 60s, showed that even in a abelian gauge theory, namely basically QED rather than QCD, we see confinement of charges in the sense that potential is linear by binding the charges. So we generate mass gap dynamically. And then soon after, in early 70s, 't Hooft beautifully solved QCD non-abelian theory with showing one Regia trajectory for fundamental fermions in this non-abelian theory. And this was done long time ago. So to gauge how long ago, you can probably imagine how old were you during the time of this work. And if that was done back in those days, then the question is, why are we talking about it here? Shouldn't all these questions about 2D gauge theories be answered? Because what these people did was even in non-supersymmetric systems. So supersymmetry, again, provides you with more control. So why are we talking about it here? Well, surprisingly, this has not been explored, and to me it's not entirely clear why, but part of the reason is perhaps that when you talk about supersymmetric systems, supersymmetrization of gauge fields of course requires you to introduce adjoint representations of the gauge group, and matter in adjoint representation is quite a bit harder. So if you're speaking about non-supersymmetric systems, then already in late 80s it was and early 90s noticed that the systems are kind of delicate. So I highly recommend this beautiful paper by Gross, Klebanov, Matitsin, and Smilga, screening versus confinement discussion, which is really beautiful piece of work on the subject. And again, there are many papers which point out that, first of all, as quarks become massless, which is what we're going to consider later in the talk from QFT perspective, things get really interesting, and it's sometimes hard to say what exactly is the phase of your system. So that's part of the reason they advertise the screening versus confinement perspective, which was recently revisited by a couple of groups using some modern techniques of generalized anomalies. And indeed, in the non-supersymmetric world, to which this 0-1 theories are very close, it's actually good to think about all these delicate questions through the perspective of generalized anomalies that we'll see later in this talk in more detail. In the supersymmetric world, indeed, if you have high enough supersymmetry, then it helps quite a bit, and with high amount of supersymmetry, things are easier and more constrained. But if you lower the amount of supersymmetry, then again, dynamics can be fairly wild, and making precise statements or even predictions becomes more challenging. So the 0-1 world lives basically at the interface, right? It's pretty far from simple non-supersymmetric systems, and equally far from very supersymmetric systems where, again, you have a degree of control. So this perhaps is some explanation why this is interesting from QFT perspective, and maybe why until so far not much is known about it. But I view it as a good thing. It means that there are lots of research opportunities roughly in this area. And this surprising perspective is basically perhaps my own surprise that encountered when with Pavel and Apogee, we started exploring this two-dimensional 0-2 super QCD, and not much was known about non-abelian gauge dynamics, despite decades of work on even non-supersymmetric theories for some of these reasons. So let me remind you what 0-2 super QCD looks like in 2 dimensions, and this will be a good motivation or platform for 0-1 minimally supersymmetric physics, which will have some parallels with a 2-dimensional 0-2 world. Now, in 0-2 case, you have basically 3 types of building blocks, namely the gauge multiplets, vector multiplets. We'll take only one because we're trying to build super QCD, so there will be SUNC gauge group with some number of colors. But then there are 2 types of matter multiplets. There is a matter multiplet which carries scalar fields, and that one usually is called chiral. And then there is a matter multiplet which only has fermions. So that's usually called Fermi. So therefore, you can have some number of Fermi multiplets, some number of this bosonic or chiral or scalar multiplets. And if all numbers are generic, you already see just from this perspective that such theories will be labeled by 3 numbers: number of colors, number of Fermi, and number of bosonic or chiral multiplets. For cancellation of anomalies, you quickly realize that the minimal version of this theory should involve yet another type of chiral multiplets and anti-fundamental representation and some number of Fermi multiplets, but the numbers are not independent, but rather related to what you chose for your SQCD to start with. Anyway, if you have these 3 numbers, number of colors, and these 2 types of multiplets, you can try to chart the phase structure. And this is a snapshot of 2-dimensional plane where number of bosonic multiplets is kept fixed, and we vary number of colors and number of flavors, this Fermi multiplets. And you see that there are many different regimes with supersymmetry breaking and supersymmetric phases where one can flow to superconformal points. And this was basically the prediction from the work with Pavel and Apogee that I mentioned earlier. In the regime where theories flow into a non-trivial conformal fixed point without breaking supersymmetry dynamically, in the language of that previous diagram, we argue that these theories actually enjoy a Seiberg-like duality. So this is partly answering the question about dualities and such minimally supersymmetric theories, in this case with only 0-2 supersymmetry, where you take these 3 numbers, you relabel them a little bit, call them N1, N2, N3, because more natural notation involves these combinations of the outer nodes of the quiver, which represent global symmetries. And then this duality is basically a statement that permutation of these numbers, N1, N2, N3, is a symmetry of the infrared physics. So there are 3 different theories which flow to the same superconformal point. In order to identify what kind of superconformal fixed point it is, in the 0-2 world, it was very useful to think about intermediate stages of this flow, which I won't be able to discuss in great detail, but I'll just mention that they involve Grassmannians, namely, in fact, complex Grassmannians, which are Grassmannians of planes in complex dimensional space, which can be represented as homogeneous spaces where you take unitary groups, say UN divided by UK times UN minus K. What I'm going to tell you about 0-1 theories is going to rely on the real version of such Grassmannians, what I call real Grassmannians, where unitary groups or special unitary groups are replaced by orthogonal or perhaps symplectic versions. And in many ways, what I'm going to say about 0-1 theories could be viewed as a real slice of 2-dimensional 0-2 theories. So therefore, as we're exploring the landscape of such 0-1 theories, it often is a good idea, that's one of the slogans that I'll try to motivate in this talk, to think about their dynamics and various properties as, roughly speaking, real slices. Not always, of course, it's going to be extremely accurate, and in fact, I don't think it's ever really accurate, but it's a good way to think about it, because many ingredients which are roughly real slices will show up, and real Grassmannians versus unitary Grassmannians is one example.
Thank you. One question.
Yeah.
What sort of bundle do the fermions form over the real Grassmannians for 0,1 theory?
There will be close analogs of beloved tautological bundles and quotient bundles. So a lot of, in particular in this story that will involve the Grassmannians, many things will be extremely similar. Unfortunately, also many things will be different. I mean, there'll be new elements, but as far as this part goes, it's really, to me, quite magical. And I myself should admit that I didn't fully, or at least as fully, appreciate the role of these Grassmannians as probably you did back in the day, because these were just intermediate stages of flow, so it's hard to know if they really capture deep physics in the infrared. But surprisingly, it's surprising how much they do capture. So yeah, we'll come back to more discussion of the bundles of this. Yeah. And by the way, feel free to interrupt me at any point, ask questions. It's more important to me that we have some discussion, or you understand everything I'm trying to convey, rather than march along. So in the context of, in comparing this 2D 0-2 theories to 0-1 theories, I also want to mention that another angle of attack. So today I'll give you many different angles of attack, or ways of looking at 2D 0-1 theories. So again, for younger people who look for projects, this could be a treasure trove of different ways of doing it. So yet another way is, suppose you know 2D 0-2 physics, you could try to softly break supersymmetry. That's a very standard trick, in fact, and try to ask what happens if you flow to 0-1 theory. For instance, in the case of three-dimensional theories, Shamit Kachru and his collaborators, the Stanford group, they basically apply this sort of technology to study non-trivial, interesting particle vortex type dualities and bosonization in 3 dimensions without any supersymmetry. So eventually they flow all the way to n equals 0 by breaking SUSY from very familiar 3-dimensional n equals 4 mirror symmetry to its less familiar n equals 2 variant, and then eventually to n equals 0, which until recently was really quite out of reach. So here, you might imagine applying similar strategy and perhaps learning about physics of 0-1 theories, in particular this real slice perspective that I mentioned a moment ago, by literally just trying to implement this soft SUSY breaking. But I want to warn you that it's not going to be as straightforward. It's going to be a little bit more interesting, because these theories are non-chiral, and here the fact that they are chiral will basically means that we cannot just completely ignore certain things and decouple certain sectors because of anomalies. So here chiral anomalies will tell us that if we want to do this soft SUSY breaking, we probably should treat these anomalies very carefully, and maybe split theories into 2 copies or TQFT that carries away some amount of anomaly. So this would actually be more interesting, at least in my opinion, that what happened in 3 dimensions where this was not a concern. And speaking of anomalies, I want to mention that that's yet another motivation for studying 2-dimensional 0-1 theories, because many decades ago, in 90s, I believe, Stolz and Teichner made an interesting conjecture that space of such 2-dimensional theories should be related to mathematical theory of topological modular forms. So 2-dimensional 0-1 theories can be characterized by their central charges. That's a basic physics of conformal fixed points. And this gravitational anomaly or gravitational central charge is conserved along the RG flow. And the number d, which is twice this difference, will be useful throughout the rest of the talk. So Stolz and Teichner proposed a connection to TMF such that if you interpret it physically, which actually until recently also has not been done, and even in this direction, a lot of work is needed. But if you try to go about it, it actually predicts a lot of interesting facts about the space of such two-dimensional theories. It basically says that the space of theories with 0-1 supersymmetry and fixed value of this gravitational anomaly has many connected components, and they're classified by this spectrum of TMF, which for various values of D could be either Z or Z2 or Z24. And in some cases, we know how to interpret this classification. For example, these two Z2s can be interpreted as fermion anomalies, where you look at a supercharge and its kernel mod 2 or something like that. So this is basically mod 2 fermion number. But physically, we know very little about high generalizations either in this direction or in this direction. So for example, Z24 is an interesting number. And as you go higher, there will be lots of these cyclic groups whose order is product of 2s and 3s and their powers. And this is extremely rich and interesting story. So to understand this story, you want to study the landscape, and you can try to test this conjecture by first asking, well, first of all, can I realize all of these distinct classes? So many of them can be realized as sigma models. So here, sigma of something means that it's a sigma model, for example, on a circle, on a T2, on 3 sphere. That's why their central charges go as 1, 2, and 3, and so on. And you can see that many of these interesting theories can be populated by sigma models on various homogeneous spaces or group manifolds. That's basically motivation from the perspective of anomalies, to which I'll come in a little bit. So
Sorry,
another
Sergei,
motivation.
one question. In the previous slide, what is X here? Some of these, entries in the second column have Z of X, Z2 of X.
That's right. So I would say let's not worry about it now. That's the answer for the TMF, and I would say let's not worry.
Is there some extra global symmetry? You want global symmetry or something like that?
Not really. For example, here, right? So it's related to. So there are several versions of this TMF. So here I'm giving again the answer, which is perhaps most familiar to mathematicians, but for more direct application to physics, there is another version where this axis basically disappears. So, and for instance, in degree 4, this would be a factor Z. And this Z is anything that is not torsion is actually visible in the elliptic genus. So I should say that this class is a refined elliptic genus. And what happens when you see the Z factors, that's where this X appears most of the time. You actually get, for example, here it would be E4, the Eisenstein series that generates this degree 4 free factor. Then in degree 8, we should expect analogous Z. Here is this guy. In degree 12, this is the modular discriminant, and so on and so forth. So many of this it's easier not to think about the X in this version, but consider a version which is quotient, where there is no X.
So another question is that, given that the conjecture is saying that 0,1 theory is the connected components of the space of 0,1 theory should be in one-to-one correspondence in topological modular forms. The 0,2 theories, the space of 0,2 theories would be similarly or even more constrained, right? So in particular, some of these disconnected components should have enhanced symmetry. Should I think of it that way?
Yes, you should, but So I totally agree with the second part. As for the first part, I want to point out that this is a very good question, and it's actually not obvious that there should be more constraint, because what happens here is, if you try to think about this connection that they proposed, so unfortunately they're not physicists, so, or fortunately, I don't know how to say, so they didn't propose very precise connection. If you try to think about it, the statement that roughly one wants to say, again, very roughly, that there is a lot of work needed to make it concrete and precise, is that space of theories with such and such symmetries, meaning, for example, supersymmetry, if there is a global symmetry, you will probably want to constrain that as well. Modular deformations is this TMF space.
Okay.
So that's actually a very spectacular statement by itself, because this TMF space carries a lot of algebraic structure. Much of it I actually have no idea how to justify in the case of physical 0-1 dimensional, QFTs in 2-dimensional with 0-1 supersymmetry. So that's already a surprise. Second, notice that it's a statement you take, it's a quotient. You take a space of theories, modular deformations. Now, suppose we want to upgrade 0-1 SUSY to 0-2, which is what you suggested. It's true that numerator will be more constrained now, because only 0-2 supersymmetry is allowed, but also denominator will get more constrained. So how it plays out on the quotient is not obvious. So therefore, what you're basically asking is, what is 0-2 analog of TMF? And naively, I at first thought that, oh, it should be more constrained. It should be not as rich. But actually, in the end, I don't know. It may be just as rich as this one, because denominator also gets smaller. So it's also constrained by SUSY.
And in their conjecture, first of all, I don't quite know what these topological modular forms are. Maybe that will take too much time to explain now. But in their work, how does, these are, as you say, mathematicians, right? So how do they incorporate the fact that, what they are talking about is some supersymmetric theory? So there's some particular supersymmetry, the Lagrangians that, you make theories with the vector multiplet, chiral multiplet. So all these things, is that how does that get into their work? I mean, how do they think about supersymmetry, I guess? I mean, this motivation, in order to make this conjecture, they need to understand both sides, right? So what is their way of looking at supersymmetric 0,1 theories? Just want to kind of see where is this kind of coming from.
So I can give 3 answers. So I'll answer now. I'll mention bookmark to this point a little bit later, in a few slides down in the talk, where it will be easier. And then I'll be happy to discuss third time after I'm finished, because I don't want to take too much time. But to answer now, all I can say is that they actually were not thinking about 0-1 dimensional QFT. They try to learn what it is, and they learn that supercharge is an operator that acts from space to space. There is Z2 grading, and so on and so forth. So that's easy. So they actually try to learn what physical theories are. Of course, this basically you can only explain so much, namely what free theories are, really. So they had a little bit of intuition, but this is, to me, a very superficial connection or intuition. Where connection is much deeper is really in elliptic genus. So they knew that 0-1 theories contain this cool quantity that we call elliptic genus. Mathematically, they understand it extremely well, especially for sigma models. That's a completely geometric object. For this, their mathematical intuition is perfect. And then they saw that in the study of modular forms, there is a refinement or candidate for refinement of elliptic genus. So therefore, they just went ahead and made the conjecture that, oh, this more advanced form of life should have something to do with 0-1 theories. That's really it. That's what happened. So.
Because a priori modular forms is something that one would associate to just non-supersymmetric partition functions, right? Or not?
Non-supersymmetric, why?
I mean, just because they will have modular property. So this is because this is a kind of a more constrained object. They went on to conjecture that it should be like elliptic genus. Is that?
Oh, you mean just to make sure I understand? So you mean characters of CFTs, non-supersymmetric CFTs, would be modular forms? Is that what you?
Partition functions. Partition functions.
But then there'll be functions of tau and tau bar, right? So here everything is function of tau. So this is definitely chiral.
Yeah.
So that's already was hint for them that it's. And again, actually, their prior work was in elliptic genus. So they were, before this, they made this conjecture that there should be connection to TMF. They were actually working on elliptic genus. And as physicists, we would probably not pay too much attention because, well, that's nice that they're understanding how to compute elliptic genus for sigma models and so on. So they built a lot of experience there, but then they noticed that elliptic genus has a refinement. And then that's basically how the story goes. So now the ball is in.
Sorry, the refinement you're talking about is by what? Because this is just a function of tau, right? There's no other variable here, right?
There is no other variable. That's right. Yeah.
Just I see.
Yeah. That's why refinement is in a sense, for instance, that whenever you see Z, that's completely captured by elliptic genus. So in fact, here you see I don't have this X in this form, a shorter version of the table. It's like the other table, but for the quotient TMF. So here, if you see Z, it means that, oh, you can definitely detect it with elliptic genus. But it's basically, for example, in degree 4, that's E4, the Eisenstein series, the fourth one, and so on and so forth. But refinement in the sense that sometimes you see torsion, and these are some global anomalies. That again, many of them we don't know. Okay, so one last thing as a motivation, I try to give different perspectives on the 0-1 theories, and I promised many different perspectives. So one last comes from a slightly unexpected place. So there is a lot of work in 90s, in particular by these two gentlemen, Ron Fintuschel and Ron Stern. And one of their papers, which is kind of a survey paper, has this intriguing title, which I'm not sure should be viewed as optimistic or pessimistic, but it poses a question about very rich geography and botany of four-dimensional manifolds. And this is the plane that usually accompanies this sort of question. So another source of constructing two-dimensional 0-1 theories is by compactifying six-dimensional 0-1 theories, which have a lot more SUSY, and for this reason were subject of a lot of recent work and classification. So if you compactify such theories in 6 dimensions on a spin 4 manifold, then you obtain a two-dimensional theory that depends on a 4 manifold. Sometimes it's called theory T of M4 or something like that. So therefore, you have a lot of choices for the starting point. You have a lot of choices for compactification. This is baby version of compactifying on spin 7 manifold that we discussed in the very beginning. And again, you can explore a landscape of theories in this way. So just to illustrate, if you have, for example, free theory in 6 dimensions, say pure 0-1 hypermultiplet, then in 2 dimensions, you obtain either some number of Fermi multiplets or some number of chiral multiplets. This can be easily done by KK reduction because this theory is free, but it actually depends on the signature of this 4 manifold. And because Rochling tells us that signature is divisible by 16, the sigma over 4 is always multiple of 4, so it's actually integer, and it's nice. But as you can see, it's already becoming, even in this free case, interesting, and depends on topology, of course. If your theory is interacting, then this is much more fun. And identifying this sort of compactification or RG flow across the dimension becomes a very interesting problem. In great generality, of course, all you can say is usually just anomalies. And again, the same number that we saw before, the global gravitational anomaly or chiral anomaly, can be extracted from universal part of the 6-dimensional anomaly, which for 0-1 theories has 4 coefficients, usually called alpha, beta, gamma, and delta. And then C left minus C right is essentially a particular combo of this alpha, beta, gamma, delta, and signature, as well as early characteristic of the 4 manifold on which we're compactifying. Now, if your 4 manifold is scalar, then you can say a little bit more. You can say individually what C left and C right are. And again, that's a very rich territory to play with, to explore this landscape, and much of it has not been really explored. What's interesting is I'll show you maybe one application of this sort of compactification on the four manifold. First of all, there is a lot of topology and geometry of four manifolds that Van Tuchel and Stern show in that graph in that plot. There are universal constraints on what four manifolds can be. And then there are also constraints on this coefficients alpha, beta, gamma, delta from various unitarity type bounds, such as information theory bounds, Hoffman-Maldacena bounds, and so on. And you might imagine that what mathematicians tell us and what physics tells us should align. Usually physics and math go hand in hand. But it's curious that in this problem that I mentioned, compactifying on a four manifold and then asking for this bounds, you carve out completely different space in this space of alpha, beta, gamma. So here is projective version where we consider gamma over alpha, delta over alpha, and beta over alpha. And blue stuff is the bounds coming from math. Red bounds is red stuff is bounds coming from physics. And in a bootstrap style way, they overlap over this island. So this suggests that maybe there is something interesting in this island, and one should look closer. So I'll just leave it at that. So there is a lot of interesting questions one can ask. But now let me come back and tell you a little bit, after all of these motivations, different angles and perspectives, something specific about one theory. So namely super QCD with 0-1 supersymmetry. And just like in 0-2 world that we reviewed, there are basically two types of multiplets. There are real slices, no pun intended, and again, using that analogy of what we saw in 0-2 case, namely there is a scalar multiplet which carries a scalar and a fermion. There is a Fermi multiplet which carries only one Majorana-Weil fermion, and then there is a 0-1 version of what in 0-2 case one would call J interaction, superpotential, which is basically coupling between Fermi and some function of this bosonic multiplets. And then, of course, if we want to build super QCD, we want gauge multiplets, vector multiplets. They contain gauge field and Majorana-Weil Gauginos, these lambdas. And to such theory, one can first of all add a generalized theta angle, namely couple this theory to TQ of T. And such generalized theta angle in general will be classified by choice of TQ of T, which is this omega-2 spin-Bordism group. And this may have various Z2 factors, so we'll see some examples in a second. Plus, we also should worry about chiral anomalies, which have perturbative form that I'll mention in a second, but also there could be global or non-perturbative anomalies which are captured in analogous fashion to this generalized theta angle by three-dimensional TQFT. But first, let's consider perturbative anomalies. This is the textbook material. They're given by this fermion loops, analogs of famous triangle diagrams in 4 dimensions. Here there are basically digons with 2 vertices. And depending on what kind of fermions or these 3 types of multiplets carry, we get either plus or minus the Dinking index of the corresponding representation. So that's fairly standard, fairly traditional. And of course, if we want to build super QCD, we want to ensure that perturbative anomalies vanish. But then there are also non-perturbative anomalies, and to understand them, so I mentioned them in terms of these fancy Bordism groups, but this is actually in 2 dimensions something quite familiar, especially if you think about the 0-1 theories as wall sheet theories on, say, heterotic string, which is yet another application of 2-dimensional 0-1 physics. So just as I mentioned earlier, we can start with the UV theory, which is a gauge theory. Then by mechanism analogous to what Schwinger taught us, we quickly proceed to a description in terms of effective sigma model, where there is a target space X and some bundle of left-moving fermions, traditionally called E, that can further perhaps flow to superconformal field theory that we wish to understand. So in this description, in this intermediate regime, sigma model type regime, the anomalies that we're talking about are standard anomalies of heterotic string. So first of all, the total bundle of left-moving fermions plus the tangent bundle of this target space should be orientable. And this is the constraint that we see directly already in 0 dimensions and compactifying this 2-dimensional theory all the way to 0D. Just the usual integral over the space would not make sense unless this is orientable or this Stiefel-Whitney classes match. Also, by compactifying 2-dimensional sigma model to 1 dimensions, you learn that these two Stiefel-Whitney classes have to align. That's a quantum mechanical constraint. And the third constraint is really a 2-dimensional constraint, which is a statement about Van Trigen classes or Stiefel-Whitney classes of degree 4, as it often can be reformulated. So let me give you an example of exactly this sort of RG flow with 3 different regimes, where starting point is a gauge theory, intermediate regime is a sigma model, and then it flows somewhere. So this is a toy model for real QCD. I mean, SQCD in 2 dimensions with 0, 1 through Z. So the gauge group is going to be Z2, and we'll take n scalar multiplets and only one Fermi, imposing the condition that sum of squares of the scalars is equal to constant. So in other words, this defines as a target space in this intermediate regime a sphere. But then we're going to gauge Z2 symmetry that flips the signs of phi's. So therefore, the quotient of a force of this n-1 dimensional sphere by Z2 is going to be the real target, which is the real projective space of dimension n-1. Now, from what I mentioned on the previous slide, all the standard heterotic type anomalies in the sigma model language would say that in this case, there is no left moving fermions. So therefore, I mean, the bundle is trivial. So basically it means that W1 of the target has to vanish, W2 and W4 have to vanish. And if we expand this 1 plus x to the n, this generator of Stiefel-Whitney classes for real projective space, and require that coefficients in degree 1, 2, and 4 vanish, we will learn that n has to be congruent to 8, or 0 modulo 8. So basically it has to be divisible by 8. Only then there is no global anomaly for this RPn-1 sigma model. And here I'm trying to do it, first of all, in the language which is perhaps more familiar, using old-fashioned traditional anomalies. Now, in the modern language, you would say that the spin 3 Bordism group of BZ2, B is a classifying space of Z2. That's what's classifying SPT, symmetry protected topological phases in dimension 3, is actually Z8. And that's actually the gauge perspective on this anomaly. A single chiral multiplet will contribute +1 to this anomaly. And that's why if we have n, which is multiple of 8, the anomaly vanishes from the gauge theory perspective. But you can see that along this RG flow, these subtle global anomalies match in a sense that in the UV, it's a gauge theory anomaly. In the intermediate regime, it's same anomaly can be understood as a sigma model anomaly. And these are kind of things that you have to worry about and work out very carefully if you want to analyze this 0-1 RG flows. So here is the bottom line, if you wish. Now we are ready to put everything I said together from the beginning, as well as this more latter part of the talk. And we'll build SQCD with 0-1 supersymmetry by taking some number of colors. So this circle is a gauge node. It represents S, U, and C. And there will be 3 types of flavors, which by analogy with a 0-2 story will be labeled by N1, N2, and 3. Here the dotted lines are fermionic Fermi multiplets, but now only of 0-1 supersymmetry. And the straight lines are scalar multiplets. The only difference is that just as was announced and as we already saw several times, this story is basically real slice in the sense that each multiplet is roughly half of the multiplet of 0, 2. And also the gauge groups are basically SO symmetries rather than unitary or special unitary groups. But one interesting thing that APGIT will immediately recognize is that, for instance, relation between number of colors here to this N1, N2, N3 is actually identical to what was in 0, 2. This is quite surprising because there are lots of small shifts here from SO and so on and so forth, but then eventually the answer comes out to be exactly in the same form. Why this is at a deeper level, I don't know, but it is what it is.
So, Sergey, in the 0,2 case, the number of sigmas was not an independent number, right? But here, a priori, is something that you can tune, the number of adjoint Fermi multiplets. Here, I guess you took it to be only one, because previously it was supersymmetric. Oh, is it related? Sorry.
Well, previously we had determinant representation. So sigma here, sigma is actually constrained. So it has to be one, at least in the version that I know. I mean, there could be generalizations. And again, of course, like I say, I'm just scratching the surface. I'll give you one example of this theory, and probably there are zillions of others. And even here, I won't be able to be as precise as in 0, 2 world. So sigma is a symmetric representation and of the gauge group. So that's this SON3, the middle thing. And it's only one. In some sense, it's basically, you can think of it as a remnant of 0, 2.
Yeah.
If you're trying to project 0, 2 vector multiple 0, 1, it's kind of remnant of adjoint Fermi that lives on 0, 2, which right. Now we were kind of not having. Yeah, so that's perhaps a better way to think about it. But right. It has nothing to do with determinant guys.
Right. No, but because it's a remnant of that guy, but they are not related anymore, right? So now they can live in the different, like for example, here it's in symmetric representation, not the antisymmetric, not the adjoint one, right?
Correct.
Yes, so it could be multiple of them also. I mean, there could be number of them also. I mean, a priori, just in the theory.
Yes.
Right?
Yes.
Then then the small N3 would be different number there.
That's right. Then N3 would be different number, and again, that would be slightly different theory in the sense. First of all, I wouldn't be able to say what I'm gonna say in the remaining 2 slides, but this doesn't mean by any means that it's not interesting or one should not, or it's I guess. One way to interpret your comment is it's hard to say what is more natural analog, and they're both actually quite natural, and one can try to vary this number. Yeah, I totally agree. Yeah.
Okay.
Yeah. In fact, I think at first we didn't include the sigma. So of course, things didn't work out in terms of anomaly cancellations, and one has to ensure this more subtle discrete anomalies also vanish. But then it wasn't entirely clear that indeed there should be one sigma, or there are other ways to do it. Yeah, that's a very good question. Right, so then there are these discrete theta angles, which I'm gonna not dwell too much on, but I do want to point that in this theory, there is also a choice of this superpotential, which is consistent with all the symmetries and gauge invariants and so on. So this is kind of important. So there is analog of what one sees in 0, 2 case, but one can also add these terms with coefficients A, B, and C. The real coefficients here are A, B, and C. And this is a little bit of a headache for the following reason, that if you look at the physics of this, the phase structure of this super QCD with this real A, B, and C, you see that there are completely different phases. First of all, it depends only on the ratio. Oh, I still have this potential here of A, B, and C. So what matters really is kind of projective version of the space, let's say C over A and C over B. And then depending on which quadrant you're in, physics is quite a bit different, completely different here. In particular, if you want to use the sigma model description of RG flow, intermediate stage in blue and yellow will be dramatically different. And for what I'm going to say next, we need the conjecture that yellow regions by quantum effects can be smoothly connected like this. So we want a conjecture that you can actually go from this lower right quadrant to upper left quadrant. On the left figure, it's kind of delicate because you're going through the origin, everything is touching here, so it's not clear, it's very quantum. So I illustrated by this clear writer picture, but again, that's a conjecture that this can be connected. If they can, a lot of things that one sees in 0-2 world can be employed. Namely, we have this real Grassmannians. The tilde means that it's a real Grassmannian. S and Q are precisely this tautological bundle, and Q is the quotient bundle. And if you want more details about the figure, you can ask Abhijit, because the physics here is very similar to physics of 0-2 story, with which he's extremely familiar. But again, one needs the statement that in every of these patches, the upper left quadrant can be connected continuously to lower right quadrant. If that's the case, one can combine it with these red arrows, which are mathematical equivalences of the Grassmannians. Grassmannians have this beautiful Z2 symmetry, where you can think of Grassmannian of either k-dimensional planes in n-dimensional space, or of course, equivalently, we can think of it in terms of n minus k planes which describe orthogonal space. And these are precisely these red arrows, which are much more manifest symmetries. So if stars align and then gods are nice to us, we should be able to connect also this more quantum regimes in each diagram. And then same statement holds that triality symmetry, which exchanges N1, N2, and N3 in the cyclic order, should be a symmetry of the 0-1 system. Again, it's a conjecture. It's based on several things. It passes several checks, such as vanishing of all the anomalies, including the global non-perturbative anomalies classified by these torsion subgroups that I mentioned. Elliptic genus checks out, and a couple of other things, but again, this is still a conjecture, and of course, a lot more needs to be done in the world of 0-1 two-dimensional theories. So thanks for your attention, and sorry for running a little over time.
Thank you very much, Sergei, for a very nice talk. Let's all unmute and applaud. Okay. Questions?
Hi, can I ask a question, Sergei? This has to do with the earlier part of your talk, having to do with essentially working out the spin 7 analog of the Klebner-Witten story of compactifying on a spin 7 with a D1 brane at the tip of the conifold, the singularity. So you did mention that there is also interest in actually understanding the Seiberg duality in this context. So I was actually wondering, so in addition to, I mean, as I guess a further development of the Klebner-Witten, strictly speaking, is there also some progress in mimicking the Klebner-Strassler part of the story, in which so maybe you know, like in particular, say, let us say that so spin 7 typically would have a calibration 4 cycle, a Cayley 4 cycle, and maybe one talks about a D5 brane wrapping that, and probably seeing strong infrared dynamics resulting either in a CP2 or an S5 blow up of the singularity. I mean, is there some progress in that direction?
I think all of these are extremely good questions. So my understanding is that the territory is wide open. Surprisingly, again, at this point, assuming that this paper with which I started has not appeared yet, pretty much nothing is really done. So that's a great opportunity to explore this. I think I totally agree with you that, for example, some of these geometries have 4 cycles, which are perfect candidates to wrap D5 brains and study fractional brain type story, which now includes D1s, completely orthogonal, and also wrap D5s. So that's part of my speculation that the number of quiver nodes that might be relevant is related to total number of even dimensional cycles in the resolutions. But again, I'm just speculating, hoping to pique your interest in this, and it seems like perhaps I partly succeeded. In the end of the talk, I presented this analog of Seiberg duality, which again happens to be triality. I have no idea why in dimension 2 Seiberg duality is order 3. So it seems to be kind of universal in 0-2 systems and 0-1 systems. But how it's realized in the spin 7 geometry, or what are the RG flows that take us through Grassmannians and so on, I cannot answer. So in some sense, it's great that there is a lot of field theory data that's waiting to be geometrically interpreted, either in terms of spin 7 or perhaps other incarnations or constructions of these theories. So yeah, these are all very good questions, I think.
All right, thanks. Thank you.
Sergei, in the finals part of the talk, when you talked about this triality of the 0,1 theories, and so do you also have this similar conjecture about the infrared fixed point in terms of WZW models and the cosets?
I knew you're going to ask this question, or at least wonder about it. No, that's a great question. Yes. So I think I mentioned in passing that I won't be able to tell you as much about 0-1 physics compared to 0-2, and that's, in my opinion, one of the most important missing pieces. We conjecture that there is a superconformal fixed point, but we don't know what it is. So that precise identification of what the CFT is, we actually don't have.
Yeah.
And that's another reason why I'm hoping that if one can manage to realize the super QCD in any other way, I don't care if it's spin 7 and D1 brains or some other compactification, maybe it will shed light on that question. From field theory point of view, it feels hard to attack it because, well, maybe if you come back to Caltech and can help, there is a chance we can make progress, but certainly without you, I don't see how to do it because supersymmetry is just too small, so it's hard. Yeah.
I remember, when I was thinking, I mean, when zero, in what sense 0,2 gives you more control over the theory compared to 0,1. One of the important points was that the R symmetry was related to the central charge, right? So the anomaly in the R symmetry kind of told you about the right moving central charge. And from the gravitational anomaly, you could figure out the left moving central charge. And then what kind of helped us back then is that left moving central charge was saturated by all the central charge of all the from the flavor symmetries, right? From all the flavor symmetries, you build this stress tensor.
Sugawara stress tensor.
Sugawara stress, yeah, exactly. So that naturally leads to that conjecture. So I was wondering if there is any way to test the right moving part. Because the supersymmetry is so little, it becomes a bit difficult because there's no R symmetry.
It's a fantastic question, right? I would love to know the answer and try to think a little bit, maybe not too heavily about it. But I think there are several things that were quite magical in that story. And to me, one of the most magical things is not really so much that one can use R symmetry to determine C left and C right separately. This, or at least analog of it, I can imagine in the 0-1 world. But the fact that just Sugawara's stress tensor and Kazama Suzuki model saturated everything, to me that's a magic. And I don't know, that's the part which I'm worried about most here. If that doesn't happen, then one has to work a lot harder. And then we were just super lucky in that case that this happened.
Right.
In fact, even up to present day, even 0-2 thing is a conjecture because there could be topological sector, right? One could speculate that doesn't carry. So it's still delicate even in that story. So here, could be much more so.
Sergei, could I ask you to follow up on a question Abhijit asked you about in the middle of the talk about these topological modular forms? I was wondering whether I wanted to get just some sense for how this mathematical structure might be in one-to-one correspondence with quantum field theories of various sorts. So is the idea that there is some quantity that you can show that is the idea that when we completely understand this, we'll find that there is some quantity that is invariant under certain classes of deformations, and then you can take it to some special theory and then compute it, and then it will evaluate to what the mathematicians compute. Is that roughly the thinking, or is it something completely different?
Yes, it is roughly this, I would say. I definitely subscribe with everything you said. Maybe just to say it in slightly rephrase what you said, hoping it may clarify that we already know that there is the chiral gravitational anomaly C left minus C right, this number D here.
Yes.
So for each fixed value of D, one aspect, but there are more of this conjecture, is that the space of 0-1 theories contains further completely disconnected pieces. That number of connected components for each fixed value of D is controlled by these groups. So what this means is that there are anomalies which we don't know about yet that are invariants under RG flows. Again, that's how I interpret their statement about deformations. But again, there are many ifs here or interpretations. So it seems to suggest that there are many more anomalies or indices that we don't know about. And then when the story is understood, fully understood, one of the aspects of this edifice will be precise description of these anomalies. So here I give only two, and these are the only two actually which are well understood. There's this mod 2 fermion number index. But there should be analogous statement in all of these degrees.
And is there a version of this conjecture with no supersymmetry?
No. So it's a really cool statement. And Abhijit also asked about 0-2, which when I first saw this, I thought that, oh, in high supersymmetry, things will be more constrained and we'll be lucky if some of the Z2s here survive and so on and so forth. But after thinking about it quite seriously, like I said, I realized that 0-2 actually may be just as rich because denominator is also smaller. So we're taking a quotient of something which is more constrained, but modding out by constrained deformations, and then quotient might still be quite rich and interesting. And whatever it is, I think it's a great question about 0-2. You're asking about n equals 0, which won't have connection to or at least a strong connection to modular forms because there is no elliptic genus anymore. But I don't know, see, so little is known about this relation that it's hard to say. There are several ingredients here and it's hard to say conceptually, is it really about global non-perturbative anomalies? Is it really about modularity and modularity of CFT characters maybe should it play? So it's a mix of several things and we don't quite understand what the hell it is really. So I don't know. So I don't know how much of this story will be in purely n equals 0 version. But it's a great question.
Thank you.
Sorry, Sergey, one more question. So just on general grounds, if you look at the elliptic genus of 0,1 theories, it should be holomorphic function of tau. It should transform in a particular way under the modular group. And that makes it something in the mathematical language, right? Presumably a modular form. But the conjecture then goes on to say it's not just that, but topological modular form, and the map goes backwards also. These are the two additional things that are being said here, right?
Yeah, correct. So there is that's why I call it refinement, or even I think that they would approve the use of this term, in a sense that there is indeed a map from physical theories into modular forms of a given weight and index and so on. But then there is actually you can factor this map through something that's finer. It's called this TMF class, and that maps further into modular forms. Basically, again, this factoring map is something that if you forget the torsion, you get the usual modular form statement.
Nice. So is there so a similar statement one can make about 2,2 theories on one side and Jacobi forms on the other side, right? Is that statement on the same footing as this one, or not? I mean that that there is some sort of a correspondence between Jacobi forms and 2,2 connected components of the 2,2 theory.
Right. So it's a good question, but even less is known about it, and things will be. So now we're going to be diverting from. So here the cool thing is a lot of torsion, which suggests that there should be a lot of global non-perturbative anomalies we haven't seen. So that's to me kind of magical or mysterious about this whole connection. And so far, it hasn't failed. So we studied it also in earlier paper with Kumran and weren't able to find a counterexample. So in some sense, this kind of table was trying to see, can we find a gap? But surprisingly, it stands. So I'm actually quite surprised. Now, if we move on to 2,2 theories, a couple of things will happen. So first of all, we are already increasing supersymmetry quite a bit. And I suspect that at this point, the fact that denominator in my previous argument is also shrinking is not going to save us. So we'll probably get something much simpler or more boring. I don't know, in terms of classification. I wouldn't expect as rich global anomaly structure as this table predicts. So here it's related to stable homotopic groups of spheres and K theory and all kinds of things. So in 2,2 world, I don't expect that. But to give you pros and cons, now in 2,2 supersymmetry, we have Jacobi forms, and there is actually a mathematical theory of topological, not modular forms, but Jacobi forms. But these things, the way they're phrased, I believe, somebody has to look into it. Again, it hasn't been done. Nobody ever thought about it seriously, as far as I know. Even TMF actually is just barely propagating into physics literature. But these Jacobi forms, I think we haven't even scratched the surface. And if I understand correctly, they're not directly related to 2 physics. They're related to 0-1 theories with additional global symmetries. Whether our symmetry qualifies or not is not clear to me. It seemed, but again, I looked at it very little, and then mathematically, it's extremely rich, interesting story, which again suggests it's not really about 2-2 physics; it's about something else. But here I want to pose rephrase your question, or pose an analogous question, that there is a well-defined theory of topological Jacobi forms that mathematicians know. They like it and they develop it. It's a very fashionable thing in this homotopy theory. Question is, what is its application? There is a chance it could be exactly what you asked, namely 2-2. My bet is that it's something else, but still, it's a very good question.
Okay, thank you. So, are there any more questions for Sergei? If not, let's thank Sergei again for a very nice and wonderful talk.
Well, thank you, guys. Thank you.
Thank you so much, Sergei.
Yeah, good to see all of you, and hope to see you in person
Yeah,
in
hope to
not
see you
such
soon.
a distant future.
Yeah, that would be great. Bye bye.